he was visionary enough to sense that this is going to be a new mathematics or new branch of mathematics, which is going to be very powerfully applied across many disciplines of science branches to emerge. Major problem was, is there some predictable pattern, though it has got a variation? And that is something which is a central theme of statistics.
Okay.
And that is something which struck Mahalanobis, and he started taking interest in this newly emergent discipline. And it was his fascination with this branch that led to his very tenuous, persistent effort to establish, which he did when he came back to India, a separate institution which is called Indian Statistical Institute, ISI Calcutta. And this is a world famous institute. People needed sampling theory experts. Who supplied this to the world? The answer is India. And again, within India, most of them belong to Indian Statistical Institute.
Right.
So that's the visionary character of Mahalanobis' realization.
Namaskar and welcome to this series of podcasts. Today we have a very special occasion, and that is National Statistics Day, which is celebrated on 29 June in the memory of great scholar of statistics, and his name is P.C. Mahalanobis. And today, to discuss his contribution and the tradition of ancient Indian statistics, we have with us Dr. Pradeep Apte, who is a well-known economist, a great mathematician and a linguist as well. Welcome, sir. So to begin today's discussion, I would like to ask you that could you please tell us a bit of contribution of Professor P.C. Mahalanobis?
Yeah, and of course you have to tell it in bit because it's really vast.
Yes, that is
and it's really monumental. Because statistics as a discipline has grown very steadily between 17th century till end of 19th century, but from 19th century onwards it has exploded. And it exploded for a variety of reasons, which I will subsequently talk about. But Mahalanobis, as a student of physics, doctorate students of physics in Cambridge, was very intimately linked with these developments since beginning. For example, it was in those times England had established Royal Institute of Statistics, and they had started publishing a journal which was quite uniquely called Biometrica. Metros is measurement and bio is of course biology or biological, and a very large number of applications of statistics which in a way signaled emergence of a very new kind of a branch in mathematics. And that was spurred by, or that was triggered by, one major problem in biological sciences. And of course, just as equivalent of Principia Mathematica of Newton, there was another book that was published mid of the 19th century, that is by Darwin. And it had posed a problem that there is a variety, and the variety is evolving, and it is enormously large kind of life variety. Why and how does it occur? And why and how did it disappear, and how the present form is also in fact nothing but another instance of the same evolutionary process. And there you come across a very peculiar phenomenon. There is both a continuity as well as a discontinuity. For example, there are continuity and discontinuity with mixtures as well. To give us a specific example with which probably initial inquiry into statistics was done by a variety of scholars, there was a monk whose name was Mendel, and he tried to crossbreed one kinds of peas with another kinds of peas. One kind of a peas whose grains would be pretty round and other which would be wrinkled. And they were also slightly different in color. For example, one was green, another was yellow. And if you look at their flowers, one kind of a flower was purple, other was white. So he was wondering, what if I breed them? And when he tried to breed them, and then he came across certain kinds of frequencies, which appeared rather shocking because they appeared to be so perfectly divided into 4 classes that many people thought that this is a doctored data. He has somehow made those frequency appear like that. And then people started inquiring into that phenomenon. One of the person who was taking lead in this inquiry was Sir Ronald Fisher, who is in fact considered to be one of the major founding fathers of the 20th century statistics. And it was to this debate and process that the biometric was often dealing with. And as a doctoral student of physics in Cambridge, together with Ramanujan, he was in the same time when Ramanujan was working with Hardy in Cambridge, he was keenly observing many of these development, and he sensed the significance of this newly emergent mode of mathematical inquiry. And that is something which is what we now know as statistics. It's not the case that the statistics before that didn't exist. It has always existed. In fact, it has always existed since ancient times in India.
Yes.
The term stat actually signifies state. That means the prashasan, or the rule, or the administration. And variety of aspects which administration needs to monitor, know about, plan for, provide for, are always in need of the relevant number. For example, if I were to serve with certain kind of a service for certain kind of people, how many such people exist?
Yes.
It's a number. Need for all such numbers which are needed in the course of administration was something which actually gave this a name which is called statistics.
So that is why it is called Sankhya Shastra.
That is why it's called Sankhya Shastra, and the Sankhya is something which is probably one of the largest and most significant gift of India to the world, because the kind of numbers that we use today is entirely the innovation that occurred in India and can deal with very, very large numbers. And that is something which is often witnessed in number of ways in which it gets into our, what we call as our epic text like Mahabharata.
Yes.
It talks about Akshauhini Sainya, which is a very large number. So ability to deal with such kinds of numbers, to make a sense of what they say and gauging which kind of an activity, what scale of activity would be needed, it's something that can be planned meaningfully if and only if such kind of a numbers are at your disposal, without which it is very difficult to in fact plan for. We must also note one significant kind of an activity carried out by one person who was always curious in many things, and he was also a very close friend of Newton, and also attributed for being cause of persuading Newton to write his Principia Mathematica, and that is Halley, in whose name there exists a comet. What he did was a very interesting thing, because from 1642 to almost till the end of 17th century, there used to be frequent plagues, bouts of plagues, and very large number of people died. And they had to leave, particularly those in the cities. Newton himself left Cambridge and came back to his Woolthorpe, his own village, because plague was a very terrible, massacring kind of a disease. So Halley thought of idea that how many people survived. And perhaps thanks to the method of registering the birth with church for baptista and also for burying, church had the record. So he went to several villages and found out how many people were able to survive the onslaught of plague. This is something which is in fact one of the recent examples of keeping data for the administrative purposes, because that spurred a question, what is the likelihood of someone surviving? Beyond what age? Because he tabulated them by survival at different age intervals or for different ages. And that came an idea of that some people survive, but some people don't. So what is the likelihood or what is the probability of someone surviving who happens to be in certain age interval? Can we say that those who are in this age interval were able to survive better than some other age intervals? These kinds of questions start coming up. And that also spurred a number of questions. But to deal with all this, you require a number system which is capable of handling such kinds of problems meaningfully. easily and amenable to convenient computation. And that was something which was a gift of India.
Yes.
And 12th century onwards, Europe started receiving something as what we call as the number system as it evolved in India, which was very rich, which had all kinds of facets of mathematics embedded in that. They started realizing that prior to that, European civilizations, including Greeks, who are often praised for the great geometry that these are supposed to have, called Euclidean geometry, they did not have a very good strength in number system. Consequently, their ability to measure and deal was very, very limited.
Yes.
And that had a consequence for statistics either, about which I will talk a little later. But it was a great, who is often called second Newton, that is Laplace, has in fact recorded that the greatest gift of Hindu civilization is the number system, without which we would have never been able to deal with the kind of natural cosmic phenomenon that exists
Yes.
around us. So it was these number systems which were imported from India that in fact gave a great impetus to the nature of growth of mathematics in general and particularly in statistics. So coming back to this problem of Mendel's, the major problem was, is there some predictable pattern, though it has got a variation? And that is something which is a central theme of statistics.
Okay.
And that is something which struck Mahalanobis, and he started taking interest in this newly emergent discipline, which was not recognized as an independent branch of knowledge or a discipline. So much so that when he later proposed it to Calcutta University, they said, if it is a separate subject, show us so many books on this.
Okay.
Only thing that Mahalanobis could present them was the 22 volumes of Biometrica which he had, and he said that this is what shows that it's a separate branch. But he was visionary enough to sense that this is going to be a new mathematics or new branch of mathematics, which is going to be very powerfully applied across many disciplines of science branches to emerge.
Okay.
And it was his fascination with this branch that led to his very tenuous, persistent effort
Okay.
to establish, which he did when he came back to India, a separate institution which is called Indian Statistical Institute, ISI Calcutta. And this is a world famous institute, not only now, but ever since then, because there were many needs of administration which were felt, partly because many countries became independent after the Second World War, and if those liberated colonial economies wanted to have a different path of growth, administration in their respective political life, but for which they needed data. And the data were often not so easily forthcoming. So how does one generate data?
Yes.
And it was a huge administrative political economic need.
Okay.
And to serve that need, one required very large amount of data to be collected in a short span of time. And that's where the branch in statistics, which is called sampling theory, gained tremendous importance. And the sampling theory, as we know it today, was not all that developed in those times. Number of problems started coming up. How much diversity should be captured in the survey that you make? How much amount of diversity by what number, if captured, is going to be representative enough? So this is what is called the problem of sample design, so that the sample becomes credible, usable, reliable, of course with certain margin of error. But nonetheless, this is something which was an important question to address.
Yes.
How does one generate such a large set of data? And with what time, with what cost? There was no clue to this. Because this was a relatively nascent new kind of a problem, needed a new kind of a discipline. And the gift of that sort was in fact the result that ISI contributed to the world. It became in fact a center of excellence and researches in sampling theory.
Okay.
Probably by the 1950s, there were only 3 prominent books in sampling theory. One was of course by Yates, other was by Cochrane, which came almost same time as ISI published book by M.N. Murthy. But this entire idea of conducting large scale sample surveys spread over large areas with great deal of diversity of the subject that is being sampled or surveyed about, this required a designal thinking, and Mahalanobis was the one who pioneered this, and not entirely by alone, but he in fact developed and cultivated a team of many budding young researchers around him. As a result of which now the world has a branch called sampling theory.
Oh, wow.
And Indians became in fact known around the world as the experts in sampling theory. Because in the 1950s, when the United Nations was formed to address variety of developmental different social questions, people needed sampling theory experts. Who supplied this to the world? The answer is India. And again, within India, most of them belong to Indian Statistical Institute.
Right.
So that's the visionary character of Mahalanobis' realization that statistics is going to be the most powerful branch. Today we talk of artificial intelligence.
Yes.
In fact, we have now mobile today, and you visit a restaurant and then you start looking at certain reels, and then the service providers, maybe Facebook or WhatsApp, start supplying you the similar kind of reels. How do they identify that pattern? This pattern recognition is something which is one mainstay, but this is a pattern recognition in presence of huge, almost a monstrous looking kind of a diversity.
Yeah.
So making a sense of pattern in the presence of great deal of diversity is one major daunting question that the statistics actually deals with. And all those facets became gradually unfolded as statistics as a discipline started emerging, and it discovered, you just ask me a branch, I can tell you one or major significant result in that branch which was facilitated primarily because of application of statistics.
Wow.
May it be physics, may it be biology, may it be chemistry, may it be any science. Of course, social sciences like economics, anthropology, sociology, all those data that are needed for social planning, demography, how population is growing, what is the age at which people marry, to how many number of children you have per household or per family. All these are the questions are now so easily, intelligently answerable and describable because of statistics. And the person who installed the systems for this and cultivated the required manpower skills, very high skilled manpower, through the institutional effort by establishing, not only that, but he also took all this to the United Nations. He was a consultant, and naturally all his students were eventually become consultant to world over for tackling such kind of problems, including one major statistician who later became the chairman of the National Sample Survey Organization, that is Professor V.M. Bhandarkar, was also a direct student of Mahalanobis in 1944. Oh. So is C.R. Rao, one who got the Nobel Prize, Nobel Equivalent Prize for Statistics. All these are the stalwarts from ISI, and the credit of course goes to the person who established this institute.
How did Professor Mahalanobis relate statistics with Indian philosophical thought? Because you mentioned his paper on Syadvad.
See, statistics has many facets.
Yes.
Because we are already talking of, I'll tell you at least two instances, which are very fascinating, and they still probably continue to be very important ingredient or in some cases building blocks of the statistics as we learn and teach and practice today. There is one very large question, philosophical questions, with which Mahalanobis tried to grapple with. And it is very intimately linked with Indian philosophical tradition. In Indian philosophical tradition, there is always a problem that the world as it exists today, to whom do we owe this existence of this whole cosmos, including ourselves as a life? And is it a one principle? And if it is one principle, why is it that there is so much amount of diversity in the life and the patterns of existence that we observe? Again, this coincides with the kind of problem that Darwin was asking. So, essence of statistics is, if you say what is a problem that statistics deals with, it deals with diversity. And you can talk about diversity meaningfully if and only if there is some reference point with respect to which that diversity needs to be defined. Otherwise, everything is different from everything. This chair is going to be different from this flower pot. But when we say that they are different, in what respects are they different? Are they not the physical things? They are. Are they not made of at least some things common, at the same time some things not so common? That's where the whole problem emerges. That there is a commonness in many existence, but there are also equal number of uncommonness, so to say, or what we call diversity. So how does one make a sense of diversity? You require to define something as a reference point to comparison. So what is statistics? try to deal with something which is common precisely to understand something which is not so common. And that's the reason why statistics is taught with first, even in the first elementary descriptive statistics class. What we teach is what is called measure of central tendency. In simple words, something which is common to all, or could be believed or observed to be common to all. But we define this precisely to understand what is not so common to all. That is what is called respectively mean, something which is common, and something which is not so common because it varies from the mean is called variance. These are the two parameters which are in fact two essential legs on which any statistical distribution, to use a technical term, has to walk with. Without this, you cannot think statistically. And when there is a diversity, the underlying problem is deeper. When we say diverse, to what extent should we try to grapple and define and describe this diversity? That itself is a big problem. And depending on which element you consider to be more important, less important, to be included, not to be included, and when you start comparing between these things, sometimes it happens that both of them are there, one of them there is, but the other is not there. So how do you define what we call a very unique classification problem? And when you say something is true, you imply often something is not so true or straight away false. But there could be an intermittent thing. You believe it is true, but maybe it is not true. Now, this kind of a problem in knowledge, which is partly a problem of classification and identifying things as unique in themselves, distinguishable from the others or not distinguishable from the others, therefore put them in the same class, is one major problem. And one discipline, or rather one major influential philosophical thought in India which dealt with this problem all the time, actually it was not one, there were many, but one which came up with this proposition that the world is very complex, as a result of which we are never able to reduce it to few categories because there are likely to be many more categories. And because there are likely many more categories about which we are never completely sure, our knowledge is going to be also equally unsure. This is what is called Syadvad in Jain philosophy.
Yes.
And its way of describing the diversity is in fact very beautiful. It says Anekantavad. Anekanta means there are anek, this is not one, there is no unique characteristic. And it may be the case, depending on from which perspective what you observe, your characterization will differ. And if that is the case, how do you unify many such kinds of viewpoints and many such kinds of characterization which emerges from that viewpoint? And sometimes it may be so difficult or so complex that you will not be able to uniquely identify them. And in that case, because you are not able to identify, all that you have to say that maybe it is not, but maybe it is. So you are not very sure of in characterization. To give a concrete example, there is something, usually we are taught in school that there are three states of matter. There is a solid state, there is a liquid state, and there is a gaseous state. But what if you observe an object which is a combination, like for example, now we deal with this matter very concretely in electronics. There is something what is called liquid crystal. Crystal is evidently a property of being something like a solid, at least in shape, but it is liquid. Fine enough, so you have got a crossbreed of these two. But this liquid crystal entity behaves uniformly as an entity in all the time, in all the places, when confronted with all the forces or matters. That's not the case. If you apply something like, say, electromagnetic field and keep one liquid crystal there, some part of it behaves differently, other behaves differently. One point it is behaving one way, but you just put it into a different kind of exposure, it behaves differently. So your ability to judge it and uniquely characterize it gets inherently complicated and in that sense impossible. And admitting this possibility of difficulties of characterization is one of the essence of the Syadvad.
Right.
This evidently has an implication for what we call as a problem in inference. That something is true and therefore something is false. or other way around. But statistics happens to be a discipline which never claims so. In fact, it most of the time says that I believe in this hypothesis, therefore I don't believe in all other claims, which may also be the hypothesis, with me being wrong so many number of times. No one claims usually in ordinary life, say that maybe I am right, but I am going to be right 95% of the time, but I admit that this is prone to 5% of the time me being wrong.
Right.
This is inherent to statistics because of inherent problems of a character of being something that exists, at the same time the incomplete character of the knowledge that we possess. So to expand the horizon of this problem of inference in statistics, Mahalanobis was toying with the idea of trying to combine this Anekantavad and the Syadvad of Jain philosophy with the problem of inference. And there is a very beautiful paper of him. Maybe sometimes we make a separate lecture on this.
Certainly, why not?
And because there was another person who was working with Mahalanobis at that time, JBS Halden, who responded to that and said, or further took over this theory and said that this is what it would mean if you look at it statistically. So this is one major connecting point of Mahalanobis, of his familiarity and fascination of Indian traditional thought in philosophical sense. Wow. Second major thing is that, in fact, he named a journal published by Indian Statistical Institute. It is of course still there, and it is now published in 3 series, which is called Sankhya.
Right.
Because that's the word and that's the gift that India that we talked about earlier. Third major thing which we should be aware is that when we are dealing with statistics, as I explained, statistics has to deal with at least 2 characterization of phenomenon that it observes, either numerically or qualitatively. One is something which is common and something which is not common. This non-commonness, this diversity is so enormous, that is one major source. That's the main spring of what can be called as uncertainty in life. And therefore, what is statistics? Trying to deal with the uncertainty for whatever its sources, and ability to grapple with that uncertain kind of a situation means diverse kind of a situation, and therefore you can't say what will happen with certainty. So dealing with uncertainty is something which is essence and soul of statistics, and all mathematical probability models are primarily meant for dealing with it. And that is typically done with 2 parameters, a measure of variability and a measure of something which is common. And they are respectively called arithmetic mean and variance. These are the technical terms for it. Let me use the simpler terms. Something that we call, and what we are taught in school, is sarasari.
Yeah. That's
a common word used in Hindi, Marathi, etc. What is sarasari? We are actually taught this in 5th standard. Given 5 numbers, add them up and divide by 5. If you are given 7 numbers, again add them up, divide by 7. What is not taught at that stage, because it is a little more intricate to teach, why divide by 7? Firstly, dividing by 7 is effectively saying that if I have got 3 numbers, I divide them by 3. That means actually I am multiplying each of these numbers by 1 by 3 and then add them up. Because adding and then dividing by 3 is same thing as first dividing by 3 and then adding. This is what we call the principle, commutative like principle of operations. We do this by 1 by 3, but what is this meaning of 1 by 3? That is actually a measure of probability. That this value has occurred. I observed a star at so and so position. Next day I observe it, I find it there is slight variation. So I find it at 13 degrees and 22 minutes. Next day I find it at 13 degrees and 25 minutes. Which is the correct measure? So I must have some answer to anchor my perception about how it is going to move. So what do? I add them to divide by 2. Effectively I am saying that this is also right. This is also right, but it may be wrong, and that may be also wrong, but one of them, both of them being wrong with equal probability, that means they may be right, they may be wrong. Measure of being right is half, so I am multiplied by half. That's the statistical meaning of dividing by 2 or multiplying every observation by 1 by 2. But sometimes it so happens, this is effectively arguing that all events are equally likely, which is not the case. For example, if I ask how many children on the average a family has Many of them have 2, but does not mean that there are no families which have got 7 children. Yes, their frequency may be less. But now when I take an average, I cannot believe it to be just 2. I must take care that there are some families where 7 children were wrong. Gone are those days. At one point of time, there could be 13, 17 children born per woman in the family. So what is the average number of children born in a given family? If the frequency wise, if you look at, there is a large range of numbers, then I have to tally and tabulate how many families with so many children, and so on. And the frequencies are not likely to be likely. That means I cannot divide by one number as I did by dividing by 2, divided by 5, 3. So what number should I take? I take the total number and I find out in this class, say all families having 3 children. How many of them out of 100? Suppose that number happens to be 27, then I will say 3 multiplied by 27 divided by 100. I will not divide it by 100 straight away. Whereas there is some family which has got probably 17 children, but there is only one family. Then I will multiply that 17 by 1 divided by 100. That means I will make them multiplied by a number which is proportional to the frequencies. So instead of equal probability, equal frequencies, we come to the unequal frequencies. Now let us come to a standard problem which has been dealt with in India, which is exactly the same kind of a problem. Suppose if I am making an excavation and there is in a gold mine, but the gold mine does not have uniformly spread gold. It has not lot amount of many trash things, many different kinds of metals. Then we are required to melt it, but still you don't get pure gold. So I get one block of metal which contains some amount of gold. There is some other location, again I excavate from there, and whatever that has been mined from there, I again put it into the furnace and make a block. Again the proportion of gold in this as against this is not going to be same. Suppose I get 4 such different blocks excavated from 4 different places, having different proportion of gold available in the soil, and if I now melt all of them together, and then I want to know how much amount of gold would be there. Not that first had only 20% of the gold, other had only 13% of the gold, third has probably 70% of the gold. Now I have melted them together and produced one block. What is going to be the most probable value of gold grains contained in them?
Right.
This is precisely the same problem as calculating what I called as frequency multiplied, that is frequency weighted averages. This is so ubiquitously discussed in all ancient Indian mathematical texts.
Oh, wow.
And from very ancient times. So they were very acutely aware of what we call weighted average. Making a switch from simple average to weighted average requires at least 3 lectures, because students have to get acquainted with this idea of unequal probability, unequal frequencies. But that is what has been so beautifully handled in all ancient texts, and they are aware that if I were to reach a finesse, what we call sola ane sona, highest, purest 16 grains of gold, how many pieces of this should I take so that I would be able to increase the gold content? This is a practical problem. It is these kinds of problems that have been very, very uniquely and almost universally dealt with in all ancient Indian mathematical texts. Maybe Brahmagupta, maybe commentaries on Brahmagupta, maybe Aryabhat, maybe Bhaskaracharya 1, Bhaskaracharya 2, or Mahavir, you name, or Narayan, you name a Indian mathematician, they are dealing with this problem of different proportions being combined into one to achieve a targeted result. Like I want to have 24 carat, no, but 22 carat gold. Then I should combine these blocks in what proportion? This is a mathematical problem which they are dealing with. So they were very acutely aware of the idea of weighted average, and they have illustrated it precisely with these kind of examples. Another unique example, for example, I am trying to dig a ditch because I want to build a tank. But maybe the nature of surface that I am trying to dig is something which is uneven in terms of its composition. There is some part which is absolutely a rock, whereas there is some part which is not a rock, which is a extractable kind of a mud. Consequently, the tank that you are going to build up is going to have a depth which is of uneven nature. So at the end of it, I have to know how much part is really occupied by the rock bottom as against one which has been sufficiently mined, but it is not possible to further mine it. If you build a tank like this, what is going to be the average depth of that tank? Again, same problem of weighted average. So one major gift that India already had made ready for the world for the growth of statistics, the notion of a weighted average. So if you want to measure diversity or a dispersion with respect to what? Not a simple average always, whenever possible and plausible, use weighted average. In fact, again coming to Laplace, Laplace says, what if you don't have knowledge about how uneven they are? You have no other go but believe that they are equally possible. But if you have some knowledge, you must use it. That's what Laplace is saying. So he's saying, if nothing is known, first to begin with, believe all of them are equally likely.
Yeah.
So this insight is very much present in Indian mathematics explicitly. They give a formula. They talk about use of what is called the most famous rule. In English, it is called rule of three. It is called Trairashik.
Yes.
And Trairashik gives you the proportion and the proportional content, and how Trairashik could be used for the purposes of this. This is one kind of a mean that we talk about, which is called arithmetic means.
Oh.
But that is not the only kind of a mean. Indian tradition also gives you another kind of mean, and that too from a very different branch. And that branch is what we now call, actually that is Indian music, but now we call it classical Indian music.
Yes. So, is this the only way to define central tendencies?
No way. There are several.
Okay.
But this became most popular, because it is most of the time applicable. In fact, as Laplace said, most of the time you don't have data about frequencies. Then what do? Simple average. But sometimes it is not so sensible. And Indian mathematicians were equally aware of this. Again, to give you a clue to the way they thought and the way it is being practiced, and that is practiced in Indian classical music. We are taught in 5th standard something what we call as a problem of perhaps maybe 6th standard or 7th standard. We are given a problem like this. There are two people who are working, say for example, painting this room.
Yes.
And one person, if given to him alone, he will complete it in 6 hours, and the other person who maybe is somewhat invalid or lazy or whatever or weak, he completes it in 9 hours.
Yes.
What if you take both of them and employ them to paint it? In what time the room will be completely painted? So this is what is called Kalkam-Weg, or the problem of work rate and time. This is a very peculiar situation. To give a simpler example, if we say that you traveled at a speed of 60 kilometers per hour, and the next hour you traveled at 90 kilometers per hour, and then what is the average speed and what is the average distance covered? For this you have to imagine a ratio, because it is 60 kilometers per hour, 90 kilometers per hour. So with these two different speeds, what you cover, it's something which is going to be covered, say for per minute, it's going to be different. So the right answer may not be 60 plus 90 divided by 2. Instead it is 60 reciprocal of 60 plus reciprocal of 90. Take the sum, take its reciprocal, multiply by 2. So the 75 will not be right answer, but 72 would be the right answer. This is what is called a harmonic mean. In other words, to give the example which we are often taught in school, someone who is working at 6 hours for a room, in 1 hour, how much does he cover? 1/6 of a room. The other person who is going to take 9 hours, he is going to cover only 1/9. So what you have to take is an average of this per hour rate, and then take a reciprocal. That is something which is one of the trick, and that is what is known in statistics or generally in mathematics, harmonic mean, because something which is there in the numerator and something there is in the denominator. So you have to consider both of them. Denominator goes usually exactly in opposite direction. So to consider that, you have to take an inverse, take the sum of inverse, then take the inverse of the sum and multiply by the number of observations. So if there are 2, then multiplied by 2. That becomes a right example. This inverse proportionality is something which is again inbuilt in ability to deal with Trairashik or Pancharashik. As a result of this, one beautiful application which we find in of this harmonic mean, where suppose there is a x1 and x2, then you don't add x1 and x2 and divide by 2. Instead take reciprocal of x1, means 1 divided by x1 plus 1 divided by x2. Take the sum. Sum is going to be x1 plus x2 divided by x1 into x2, take a reciprocal and multiply by 2, and that's what is called a harmonic mean. And the term harmonic mean is in fact suggestive of music. When we sing, or it is universally now so, but in Indian classical music it has been thought of and applied different with a greater depth. What is the depth? We talk about shrutis.
Right.
And most of the shrutis are generated out of not applying simple arithmetic average. So to give you the idea, there is a shadja, Rishabh, Gandhar, Madhyam, then between swar is Pancham, is middle swar, and last is again Dhaivat, Nishad, Shadja. So what is the midpoint of Shadja below, what we call Kharja, and Shadja above, which we call Tar. So Tar Shadja and Mandra Shadja, if we add them, divide, you get Pancham. A typical frequency of Shadja is 240. Typical frequency of the Shadja above is double, that is 480. Add 240 and 480, divide by 2, you will get 360. That is the frequency of Pancham.
Yes.
But if you apply the harmonic mean principle, you take a reciprocal of 240, reciprocal of 480, add them, then take a reciprocal of addition, multiply by 2, you don't get 360, you get a point which we call Madhyam.
Okay.
And that is 320. This is, so you sing by having which midpoint in mind, because in singing what do? You make a progress from Mandra Shadja to Tara Shadja.
Yes.
So what is the path? The path again requires some in-between swar. That in-between swar could be Pancham, in-between swar could be Madhyam.
Yes.
If this is true between Sa and Sa, why is it not possible between Sa and Gandhar, Shadja and Gandhar? So you can define every time a midpoint of Shadja and Gandhar, midpoint of Shadja and Madhyam, and again by two principles. If you keep doing this with the harmonic mean, you get certain kinds of different places of what we call frequencies. And if you are able to produce those frequencies either from a tar, that is the string, or from your voice, then you are capable of singing shrutis. So shrutis are nothing but one set of notes is actually coming from arithmetic mean. Other set of interpolation between any two swaras is going to be harmonic mean. If you combine together, you will get in fact what are traditionally referred to as, for practical purposes, as shrutis. Because the person who sings, he doesn't do this mathematics.
Yeah.
But what he does is he knows that from this shadja or from this rishabh, I have to raise my voice or modulate it downwards. Up to what? That up to what has a choice, and that choice is twofold, one suggested by arithmetic mean, other suggested by harmonic mean. This is one of the greatest gift and application of harmonic mean in the world. So the Indian classical musicians were equally conversant with the idea of using not only arithmetic mean but also harmonic mean.
I was about to say that I'm feeling very happy and pleased because when I sing sa pa sa, now I am a statistician.
But you also try with madhyam. There are certain kinds of rag which are necessarily sung only by not having tanpura tuned to shadja pancham shadja.
Yes, it
but
is shadja
madhyam shadja. So is the practice of Western musicians. In fact, their violins are also tuned by shadja madhyam shadja.
Yes.
Because it gives you productive potential of different frequencies that you would like.
Even for Sama Sangeeta, it is always Shadja Madhyam Shadja. It is never Shadja Pancham Shadja. Yes.
So that is another major gift and applied gift, so to say, of idea of harmonic mean taught only in statistics or otherwise frightening problems such as work, persons and rates. But this is something which is also equally plausible mean. Because all that you need is what is characteristic of a thing that you are talking about. If that is useful, you can always use it.
Interesting. Now I would like to ask you one more question, because you mentioned patterns and there are always permutations, combinations. So how can we connect this to the Vedic literature or the meters? Because today we are talking about statistics and ancient Indian knowledge systems.
Yeah, one more important gift. I talked about diversity. See, diversity also have probably two states. One is diversity which is really infinite, and diversity which is large enough, but still what we call countable, not in strict mathematical sense, but it's countable. Because many times uncertainty exists in what form? It is because many things can happen, but only one of them happens. Which one of them is likely to happen? That's what we call uncertainty. So you have to think of variety of ways in which even given elements can generate a variety. So suppose there are 3 things, they generate a variety. There are 5 things, they generate a variety. As the number of things that constitute a given phenomenon, if they can be arranged, combined in different manners, that itself gives rise to enormous diversity. Mathematical way of dealing with this is what is called the method of permutations and combinations.
Right.
And usually this is hardly mentioned in most of the statistical or mathematical texts today, but this is perhaps one of the largest gift because it gives you a method of counting. They are simply called methods of counting or enumeration, and they are enormous. And the enormity of that and the method of counting such an enormous possible configuration was in fact stated and itself configured by Indian mathematicians. Probably the one most important, shining and glorious example of that is Pingala Chanda Shastra. You know, the Chanda Shastra for Indian tradition is very important. Not only because its so-called sacred scriptures are composed in, but Chanda has an inherent mathematical structure. And one kind of a Chanda is very distinctly, definitively distinguishable from another kind of a Chanda. So when I say Gayatri and when I say Ashtagayatri, or if I say Anushtubh or if I say Arya, they signify a definite pattern. These are the names given to the patterns.
Yeah.
How many such patterns can be there in poetic composition? Poetic composition involves 2 things. Number of letters that are going to be there in one line.
Yes.
Where you are required to stop. This is what is called yati. And the sequence of vowels and the so-called sounds that we are going to produce, are they laghu or guru? That means can they be produced in 1 second or they require roughly 2 seconds?
Yes.
This is something which gives the rhythm to the poetry that we talk about. So,
And also we have Rasva, Dirgha and Pluta.
Precisely.
Yes.
So these 3 types of swaras
Yes.
are distinguished in Indian tradition. And Rasva is 1, Dirgha is 2, and Pluto is more than 2, but usually 3.
Yes.
So how do you prolong whatever that you are saying in your ucharan, that is pronunciation? That is very relevant thing for poetry, particularly for the Sanskrit poetry, because it had configured several such meters.
Yes.
Sometimes for the nature of subject and the nature of words that are at their disposal. Sometimes because its own inherent beauty, its ability to communicate,
Right.
its ability to not only communicate but also give a pattern of recurrence so that your ability to remember it becomes easy and handy. That's one of the major dominant purpose for which the Chanda Shastra is in fact practiced in India.
Yes.
Because if you want to be the scholar of Vedas, you must know Chandas.
Yes.
Because you know how to pronounce it.
Yes.
And how a given kind of a rucha would be pronounced has its own definitive rules, which English usually calls meter.
Yes.
But in fact, a better word is in fact the Chanda. Because it is not only a matra, but a collection of matras.
Right.
And that too sometimes in a pair, sometimes in a triplet, and sometimes in a combination of pairs and triplets. So how this happens is something which is important.
So essentially it goes back to Vedas again.
Yeah, it goes back to the Vedic tradition because Vedic tradition has been composed in terms of Cheda.
Exactly.
And there is a thought and a pattern, a mathematical pattern which it follows. All the chandas are not necessarily Gayatri. There are several chandas in the Vedas. And if you go look at the glorious, such a large literature, which has been, like Mahabharata is composed in chandas, so is Ramayana. All epics, all classical Sanskrit literature has one or other time always falls back on the use of chanda. Because it is easy to remember, it is easy to recite, it is easy to modulate in terms of bringing out the emotion or the expression that you want to highlight.
Yes, we have Meghaduta, which is composed
Meghaduta.
in entire poetry
the
is
entire all
composed in
126
yes,
or whatever odd,
1 meter.
all of them are only in 1 meter. And there is a rhythm to it. And though it is one rhythm, it is amenable to sing it differently. Like saying Kaschit Kanta Viragurunam Swadikarat Pramatta. But while singing, I can always prolong it. Kaschit Kanta Virahaguruna Swadikarat Pramatta. This is the way in which that meter comes handy to have your own musical exploration if you want to sing it and not say it.
So it can be tuned, right?
So it can be tuned with a different adjustment to what we call matras.
Yes.
Incidentally, metros and matras are close related in the European world. But this is something which they applied a great deal of thought and developed an elaborate mathematics of this. And this is something which is so inherent in all kinds of texts that you come across in ancient Indian tradition. Like for example, in Charak he asks a question, I have got effectively 6 major tastes. Like it is salty, it is astringent, it is hot, it is sharp, it is acidic. So all these 6 rasas, if I want to combine them, how many different kinds of tastes can I produce?
Oh,
this
wow.
is often is produced, it is often said that how many different kinds of chutneys,
yes,
or what we call English term, relishes, that can be composed out of 6 different kinds of tastes. Mathematical question.
Right.
And there is a definitive answer for this in Charak. Generally spoken, 64. But if you have used all of them, and if there is going to be same as all of them vis-a-vis none of them, then none of them may be omitted. There are 6 ways of doing that as well as this. So if you reduce 1, it would be 63. Otherwise, general answer is 64. So you can produce 64 types of chutneys out of 6 different swadas. Now he is actually dealing with Anna Prakaran. He is dealing with Arogya, that is health treatise and the methods of dealing. But remember, each of these swada or a test is also characteristic of the kind of ingredient that they are using for preparation and construction of a medicine preparation. So they are again very acutely aware of the proportion. Something increasing in test means the proportion of that particular ingredient must have gone up. And that's not the arbitrary way in which a medical preparation can be composed of. That's why they thought of this. So there are many instances. One is poetry, other is these kinds of applications. There is also another beautiful realization of this in Indian tradition. For example, there are many deities, and the deities have different kinds of powers, diversity, something which is a soul of statistics.
Yes.
The Vishnu has different kinds of powers, and different kinds of powers exercised by different kinds of instruments that he has, what we call ayudas or the astras. So when Vishnu is depicted in say a sculpture, in how many ways it can be done? Because Vishnu has 4 hands.
Right.
But each of them having different thing.
Ayudhas.
These can be arranged in different manner. This is Kamal to begin with, and this is Sudarshan Chakra to begin with, but I can always interchange. Same with the other 2 hands. Like there are 4 kinds of astras or shastras, ayudas, or for that matter, bhushanas. In how many ways can they be arranged? There is an answer for this in Indian mathematics, and there is a mathematical method of arriving at that answer.
What is
and
that
that
method?
answer is what is called permutation.
Oh, right.
There are 6 factorial, as we call it, which effectively means 1 into 2 into 4, 3 into 4 into 5 into 6, or 1 into 2 into 3 into 4 in case of Vishnu. So if it is 6 rasas, it will be 64. If it is 4 hands, each of them having alternate arrangement of the same 4 kinds of ayudas or bhushanas of Vishnu, there would be 24. So there are 24 Vishnus, Vishnu Nama.
Yes.
And Vishnu Rupa, and all of these are in fact engraved. Like for example, that Rani Bhav in Gujarat has got 15 of them, and if you want all those 24, all of them, each of the configuration distinguished by the nature of the astras and abhushanas, there are 24, and all of these are there in Chenna Vishnu Mandir in Karnataka.
Yes.
So whether it is Murti Shastra, whether it is sculpting, whether it is a method of decoration. Now imagine that if Vishnu with 4 kinds of hands and for each hand 1 distinct ayuda or abhushana, imagine of Shiva.
Yes.
Shiva has 10 hands and for each of the hand is going to have one unique distinguishable kind of an astra or abhushana. How many number of Shivas can you paint or can you sculpt? Yes. Answer is enormously large. Just I will give it as an exercise. 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9 into 10. And it will run into lakhs.
Right.
So find out, take a product, those many number of configurations of Shivas are possible. So it is not out of just a fancy that they thought of Sahasranamas, because they had a method of enumeration in each of these cases. Exactly. So there is a logic to these numbers. So much so that now the numbers become the element by which a different name is acquired by a number. So when I say loka, lok would mean there are 3 lokas. So instead of 3 they can use loka. That's another beauty in the Sanskrit and Indian mathematical tradition. So figuring out total number of what we call permutations, or a lower number where the manner in which they appear, order in which they appear is not important, to the extent there are 3h or 2h that are taken together and counted as if they are same. So the count reduces by r factorial. This is what is called combinatorics. All this is there in Chanda Shastra. Pingala Chanda Shastra is in fact a treatise. If taught, it teaches at least 30% of the combinatorics that we ordinarily teach in the introductory course on combinatorics. We teach a binomial theorem.
Right.
And that binomial theorem is nothing but an expansion of 2 terms. Usually we use a plus b raised to square, or x plus y raised to square, or ksha plus y kaus varga. If when you expand it, you get 3 terms. And they have coefficient. For example, if I take x plus y raised to 1, it is x plus y. What is their coefficient? 1 and 1. But when I say x plus y square, then it is x square, coefficient 1. 2xy, coefficient is 2 in the middle term. Y square, again coefficient is 1. That means it is 1, 1. 1, 2, 1. Instead of 2, if I take a power 3, there is an easy method of constructing it. You write it as 1, 1 and 1. 1 means x plus y raised to 0. That means the coefficient is 1. X plus y raised to 1 means both coefficients are 1 and 1. X plus y raised to 2, then the coefficients are going to be 1, 2 and 1. What is going to be x plus y raised to 3? It is bound to be 1 plus 3 plus 3 plus and 1. How did I get this 3? Because it is 1 and 2, I add them right below. Again 2 and 1, add them right below. There is nothing to add, repeat 1. So if this is the case, then I can also talk about what is x plus y raised to 4, because I have got a string which is relevant for 3 elements or 3 trials. So what is going to be for the 4th trial? Start with 1. What is the string? Previous string of 3? 1, 3, 3, 1. What is going to be the next string? Again the same principle of adding. 1, 1 plus 3, 4. 3 plus 3, 6. Again 3 plus 1, 4. Nothing to add, 1. Like this, if I repeat for 5, then I can continue like this to whatever number that you want, and it produces a kind of what we call in Indian tradition Meru. This was defined by Pingala. It was only 17 centuries later, the French mathematician, great mathematician Pascal, who discovered this principle in binomial expansion. It is taught in schools and all European dominated texts today as Pascal triangle.
Right.
Pascal triangle is a key to understand binomial theorem. And binomial theorem requires combinatorial coefficient, not permutation. And once you know this, you can expand any binomial with whatever additional coefficient to the x and y. For example, I can also find out what it would be 3x plus y square. All I have to do is I have to take the relevant power of 3 as well multiplied to those coefficients. So generation wise it is very easy. Why was Pingle interested in this? To define the patterns of meters that are definable. Now there is a very simple clue to binomial expansion as defined by Pingle in this, which we, in fact when I teach this I have to highlight this, that if the power is 3, the number of terms in the expansion would be 4. If the power is 4, number of terms in the expansion would be 5. It is always, if the power is n, number of terms would be n plus 1. What does it mean? It means that every odd number that you tell me, I can tell you what will be kind of a configuration that I should have of what terms? two terms. What are they called? Laghu or Guru or Rasva and Dirgha. And the pattern in which they are going to appear, if you bother about the order of that pattern, string is longer. If don't bother about it, club them together. If I say AB square or B square A, I'm going to say it is the same. Then I will count them as if they are same. That is combination. If you don't want it, the list will be longer. How to prepare such list is something which has been generated out of only two numbers called X and Y, or Laghu Guru, or Rasva Dirgha, whatever name you add. That's why it is two. Two is by. Nomial is name. So it is Dvinama or Dvipadi. You can extend it to the Tripadi, Chaturpadi, Panchapadi. Rule becomes same. Rule is predictable. And that is something which is the power of Pingala's Chanda Shastra. More importantly, he wrote it in terms of Laghu Guru. So whenever it is Laghu, write 0. Whenever it is Guru, it is you write 1. You get entire binary system which happens to be every electronic gadget that we are operating with. And that entire binary logic, binary expansion, binary number means ordinary number represented in terms of binary number is possible because of Pingala's notation of Laghu Guru. This is something which is probably one of the most lasting and very deep impact creating kind of a system of enumeration. India gave world decimal system, but Pingala on the top of that gave world a binary system of numbers.
Wow.
So you give me a number, I will tell you how to write it in binary terms. There is a simple algorithm for this. Keep on dividing by 2 till you finally reach either 0 or 1. And write that string of 1, 0, because whenever you divide by 2, residual is going to be always 1. And what remains as a string is in fact a list of residuals. It is this principle which gives you clue to how to use different number systems. So Pingala gave anyway binary system which we use in every electronic
so this is
gadget
another
and
significant
computer.
contribution by an Indian scholar.
Absolutely, this is one of the greatest contribution because it gives a clue that yes, we ordinarily use 10 as the base, but not necessarily. You can use any number. Which numbers? Now everyone knows that the most convenient number would be one which would be a prime number. But you want to define it in 6, which is not a prime, still it's possible. So to have a number select, for example, we use it in watch. What is a watch? Watch is going to have 12 number. What are those 12 numbers? We believe it is 1, 2, 3, 4, 12. No, it's wrong. It is actually 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12 is same thing as 0. Because that's the cycle. That's the way your speedometer works. Because you have completed one cycle, it goes one step ahead. So when we read 1, 0 in the speedometer, you have completed one cycle. That's the way in which the number system works. This was illustrated in terms of two numbers. That's why it's called a binary system. And the method of constructing a binary number for any arbitrary number which is in decimal system is also a gift of India. It is not a recently discovered idea for the purposes of computer age. It's other way around. It is the people who devise computer realize that either the electrical gate, because the initial computers were electrical, the gate is either open or closed. That means it is going to be 1 and 0. So if I have successive gates, what kind of a configuration of gates you can get? Both of them open, 1, 1. Initial close, next open, 0, 1. Initial open, 1, next close, 0. Again next open, 1, 0, 1. So this method of enumeration and putting binary system is also inbuilt in Pingala Chanda Sutra. And that is something which gives you great beautiful poetry, great meters, number of meters. Like for example, if I want to compose, like I talked about Mandakranta, which is the meter of Meghadoot. It has 17 letters. Can you have it for 19? Yes, why not?
Yeah.
Because all that you require is an expansion which has got 19 expansion terms. That is going to be the meter. For example, Shardul Vikridit. Give me a number and I can think of a meter, and all various possible combinations in triplets is the method of composing meters in India. That's why there are so many meters. We are probably taught more than 20 in school. You read any Chanda Shastra book, number of meters is typical real academic answer is infinite. So ability to deal with large number of configurations, which is the root cause of diversity. Because diversity means so many configurations. And what is the likelihood of you having a meter of 30 letters out of how many? You can have an answer. That's how we teach probability. That's how we understand probability. So I observed so many number of things, but only 10 of them were patients. So I say, yes, then the probability of someone getting a disease is 10%. This idea of enumerating the all diverse element, putting them in classes, taking their count and using that count to construct what I initially explained as weighted average mean, this is what the initial statistics course is. So in this sense, in terms of these three ingredients, India really laid the foundations of statistics.
It is really amazing to know that from tastes of chutneys, so that from cooking to music and from poetry or devatas to philosophy.
And computer science.
Yeah, and computer science and AI and so on. It is everything about maths and particularly statistics, and we are fortunate ones that we call ourselves Bharatiyas because our ancestors contributed a lot, and thanks a lot Dr. Apte for giving us all these insights, and I would like to extend our gratitude to efforts made by Professor Mahalanobis as well. So with this promise that you will deliver a separate lecture series on ancient Indian mathematics and traditions on our digital platform, that is bharatvidya.in. Let us conclude for today. Thanks a lot.
Thanks for the opportunity.
Thank you.
It's my duty and pleasure.